This video looks at modelling within predictive control. So the previous videos introduced the main concepts underpinning predictive control, but clearly these were done quite briefly and in a fairly simple human-centered fashion. Now, in order to automate predictive control, it's necessary to present these concepts in more mathematical terms and a little bit more rigour. So we're going to begin that process now. We'll start by looking specifically at modelling. Models are required in order to make predictions, and as prediction underpins predictive control, this is a logical place to start. Model requirements then. If we want to do simple manipulation and algebra, then what we really want is a linear model, because if you have linear models you can use superposition, and basically everything is a lot easier. Now, what you'll find when you look in the literature is that predictive control usually uses a linear model, but if we want to be more generic, what we're going to say is we will use a linear model whenever these are good enough. There will be times when a linear model is not good enough. That's beyond the remit of these videos, but you do need to be aware of that case. So these videos are not going to discuss nonlinear models and the associated predictive control, because that's far more complex and beyond the level that we want to go to. Now, the typical linear models you're going to come across might be transfer function models, you're probably all aware of those, and state space models. You might also come across step response models, but to some extent those are a subset of transfer functions. What about, should the model be discrete or continuous? Now, you're going to argue probably that all processes actually operate in continuous time, and indeed if you look at classical control laws such as PI, you'll find that they tend to be written in continuous time. However, here's a key point. If you look at decision making, you'll find that decision making tends to be more of a discrete process. It's not done continuously. It's done, you make a decision now and you make a decision maybe in 10 seconds time or a minute's time. And why is this? Because decision making requires processing time or thinking time, and thus it cannot be instantaneous. And if you think about the context of predictive control, you might be dealing with a multivariable system which has interacting inputs and outputs, constraints, performance, and in order to handle all that information and come up with a decision, it cannot be done instantaneously. And therefore, this is what you end up with. Common predictive control laws are implemented in discrete time. Now, you will find, if you look around, there are some continuous time variants in the literature, but to some extent I won't quite call it trickery, but you'll find they also have discrete decision making, even though the way they're expressed is in continuous time. So in practice, they all, in fact, do the decision making in discrete time. So if we're going to do things in discrete time, the question is, what sample rate should I use? Now, we need to decide what sort of sample rate makes sense. You can see for this particular example here, what I've done is I've put roughly 10 samples into a typical rise time for this response. And what you'll find is that this is typical in predictive control. What people do is they say, look at the rise time or settling time. You've really got to have a rough idea of how the responses will be before you can judge that. And make sure there's roughly 10 samples within that. And why do we say this? Because if you sample more slowly, then you're not able to get high performance, and you're not able to respond fast enough to any disturbances that occur. So if a disturbance occurs, you're not going to notice it till maybe one sample later. So you don't want that sample time to be too long, or it's going to be a while before you start rejecting it, by which time the effect on the output could be significant. Why don't we sample faster then? Well, this is the problem if you sample too fast. You can see here I've drawn an input which is changing very fast. But if you look at the corresponding output signal, you can't really see the impact of all these changes in the input. And why is that? Because real systems have essentially got a small gain at high frequencies. So if you bounce the input up and down very fast, it'll get basically filtered out and you won't see it on the output. So there's no point changing the input very, very fast. So if you had a high sample rate in predictive control, generally speaking, people would argue this is pointless. The system cannot respond to fast input changes, and also it increases the number of decision variables, which makes your optimization much more complicated. So what you're trying to do in predictive control is sample fast enough so that you can reject disturbances, but no faster than absolutely necessary, because that keeps your optimizations simpler. So the summary will be, we tend to operate in discrete time, and we're going to use a sample rate of around 1/10 of the principal system dynamic response. Now you'll notice the second assumption is somewhat loose, so it can be modified as required. Most common models then. Well, increasingly in the literature you'll find that these days people use state space models. So I've written down here a typical state space model. X might be the state, Y might be the output, U the system input, and D one representation of a disturbance. Here I've got an output disturbance rather than an input or a state disturbance. So that's a common discrete state space model. Now in this particular series we're going to assume that D is 0, so that term's going to disappear, i.e. there isn't a straight through from the input to the output, which for most systems is a reasonable assumption. Now the other thing we're going to make clear here is this is a standard or a classic state space model. Of course, in particular cases and particular scenarios, the state space model that represents your system may be just a little bit different. But if you can follow everything we do with this model, then making the required modifications for a slightly different model will be straightforward. Transfer function models. Now originally within predictive control, most people did use transfer function models. They were more popular and they focused on this thing called the Karima model. Now this subsumes in its structure many other popular transfer function forms, so that's why we're just going to give this one and not bother about other variants. And it was used because the uncertainty, in particular disturbance uncertainty, is included in a way that allows you to represent, and here's the key point, slowly varying disturbances that could have a non-zero steady state. And for certainly in the process industry, people took the viewpoint that a slowly varying disturbance was perhaps a good representation of reality. So a model structure that captured this was suitable. And this is what the Karima model looks like then. You'll notice the key thing is this term over here. So we've got the standard output Y, the standard input U, but then we've represented this slowly varying disturbance as some polynomial T of Z times zeta over delta, and the key thing is zeta is a zero mean random variable, and zeta over delta gives you a sort of random walk which represents this slowly varying effect. Now, just a warning, while this works quite well for single input, single output systems, it's a little bit more clumsy if you need to go to multivariable processes. So you will find some papers in the literature that have done transfer functions and multivariable processes, but generally, once you go multivariable, people move to state space because it's easier. Step response models. Now, within industry itself, step response models have become quite popular and were used at the outset because they were relatively easy to identify. The weakness of them is they require a large number of parameters. So that's a bit of a pain. Now, how would you estimate disturbances if you were using a step response model? This is how people tend to do it. So they say the output is given by a step response, so that's h of z is the step response, and you'll notice here that we've used delta u, where delta u equals UK minus 1. It's the change in the input at each sample, because that's what the step response does. But the key thing is this extra term here on the end. That represents an estimate for the disturbance. But what you'll find is if you estimate that term in the correct fashion, it will also take account of other things like the fact that your step response is an approximation of the real parameters, etc., etc. So this is quite a good way of capturing any uncertainty in your predictions. Independent models. Now these are not used quite so much anymore, but again you will find that sometimes they're a useful concept. The idea here is that the model G that you're going to use can be anything. It could be state space or transfer function or step response. It doesn't really matter. And you consider it in isolation from real plant measurements. And the actual future predicted outputs are taken solely by looking at the independent model. So you say, what future inputs am I going to do, or what past inputs have I got? You stick them in your independent model and you find out what it gives you. But then you add an offset term which represents the expected difference between the model and the true process. And what people will normally do is they'll say this offset term is essentially the disturbance term, exactly the same as we had for the step response model. So in summary, it's common to use discrete models in predictive control. And these models can take whatever form the user wants, your convenience. But the algorithm is easy to code and implement if you use simple linear models. Now, a typical sample rate is going to be around 1/10 of the time scale of the principal dynamics. Again, that's fairly loose. You can modify that if necessary, but generally speaking, if you go much faster, you're wasting your time, and if you go much slower, you're sacrificing performance significantly.